Welcome to This Explainer. Today, we're jumping right into the fascinating world of deep time. We're going to examine the strict geophysical mechanisms and chemical clocks that allow scientists to put absolute, concrete dates on the Earth's most ancient formations. No guesswork, just the hard science of how we actually read the history of our planet.
Here is our roadmap for today. We'll start with reading deep time, move into the atomic clock, dating ancient rocks, figuring out Earth's true age, carbon-14 for recent history, and finally, choosing the right clock.
All right, let's kick things off with Section 1, Reading Deep Time. So, moving beyond just looking at rock layers, how do we confidently point to a specific formation and say, yep, that's exactly 1 billion years old? I mean, geologists aren't just making educated guesses here. There is profound, strictly measurable science anchoring these numerical values. The secret lies in stepping past relative dating, methods like relying on stratigraphic order or the principle of superposition. Now, those principles, especially when combined with fossil records, are great. They give us a fantastic relative timeline. But to get the actual receipts, we need radiometric dating. This gives us numerical dates in actual years. It doesn't replace the geological timescale at all. It just anchors it perfectly to absolute time.
Which brings us right into Section 2, the atomic clock.
To get those absolute numbers, you really have to think of radioactive isotopes as an hourglass. But it's a special hourglass where the sand falls at a highly predictable exponential rate. We call this its half-life. Out in nature, certain unstable elements spontaneously change or decay into completely different elements. We call the original element the parent isotope, and what it turns into, the daughter isotope. So the half-life is simply the exact amount of time it takes for exactly half of those parent atoms to make that transformation.
And this basic dating equation is the mathematical engine under the hood. You don't need to memorize the math, just know that this radioactive decay is constant. It is perfectly predictable. By measuring the ratio of daughter to parent atoms currently sitting in a rock, we can effectively read that hourglass and calculate exactly how much time has passed. Seriously, whether a radioactive atom was formed yesterday or 1 billion years ago, the probability of it decaying tomorrow remains identically constant.
Let's look at how we apply this in Section 3, Dating Ancient Rocks.
Now, there is a catch. For these atomic clocks to work, we absolutely have to assume a closed system. No elements leaking in, no elements leaking out. The math only works if all the daughter atoms we measure were actually created by the parent decaying inside that specific rock. If the rock was weathered and some parent isotopes washed away, or if it was heated and daughter gases leaked into the atmosphere, well, the clock is broken. We have to be completely certain the system remains sealed since the moment the rock formed.
But when we find those closed systems, it opens up a specialized toolkit of primeval isotopes. The big three are uranium-lead, potassium-argon, and rubidium-strontium. Now, no single method works for every single rock. That's exactly why scientists rely on a whole variety of these primeval isotopes, meaning they've been around since the Earth formed, to cross-reference their findings.
Let's start with uranium-lead. This is literally the gold standard for dating ancient rock, specifically using tiny zircon crystals. It's amazing because it provides a built-in double checker. Uranium-238 decays into lead-206, while uranium-235 decays into lead-207, and they do this at completely different rates. Because zircons practically lock out lead when they first form, any lead we find inside them today absolutely had to come from radioactive decay. By measuring both pads, we're basically running two independent clocks at the exact same time. When both give us the exact same age, we call that concordant, and we know for sure that date is rock solid.
Now, for other rocks, we might use the potassium-argon method. Potassium is everywhere in igneous rocks, so it's a super convenient clock. But there's a problem. Its daughter isotope, argon, is a gas. Over millions of years, if a rock gets heated, that gas can leak right out of the crystal's vulnerable parts, making the rock look artificially young. So, scientists brilliantly developed argon-argon step heating. They put the sample in a nuclear reactor, convert some potassium to argon-39, and then heat it up in gradual temperature steps. This flushes out the leaky, unreliable parts first. Once they reach higher temperatures, the argon release from the most tightly sealed parts forms a beautifully flat age plateau, giving us the true, stable age.
And what if a rock has been completely reheated by, say, a mountain building event? That's where the rubidium-strontium clock comes in, using these intersecting lines on a graph called isochrons. Imagine a magma chamber cooling down. Different minerals crystallize with different amounts of rubidium, but they all start with the exact same baseline ratio of strontium.
Over time, as the rubidium decays, those ratios spread out, creating a straight, rotating line, an isochron. The slope of that line equals the age. But if the rock gets reheated millions of years later, the isotopes mix back up, resetting the clocks in the individual minerals, but crucially not in the whole rock overall. By measuring both, we can tell exactly when the rock was born and exactly when it was melted again.
With this toolkit established, let's tackle Section 4, Determining Earth's True Age.
Using the lead-lead dating method, we get this foundational benchmark in geophysics. 4,550 million years, or 4.55 billion years. It is a staggering number.
But what does that number actually mean? What you should really take away from this is that it dates the exact moment the solar nebula became our distinct solar system. It's the moment that chaotic, swirling disk of dust and gas spinning around the early sun finally clumped together into separate, closed subsystems, meaning the planets and the asteroids.
But here is the ultimate irony. To find the age of the Earth, we actually couldn't use Earth rocks. We had to date meteorites from space. Why? Because the first few 100 million years of Earth's existence were so intensely violent that our original crust was completely destroyed and recycled. So geophysicists looked to chondrites and iron meteorites, the pristine debris left over from the solar system's formation. When they plotted the lead isotopes of these meteorites right alongside modern Earth lead on a single isochron graph, everything aligned perfectly. The Earth and the meteorites share the exact same birth date.
Let's shift gears from deep time to recent time with Section 5, Carbon-14.
The carbon-14 cycle is just fascinating because, unlike uranium or potassium, it isn't primeval, it's cosmogenic. Energetic cosmic rays from space are constantly slamming into nitrogen in our upper atmosphere, converting it into radioactive carbon-14. Plants absorb it, animals eat the plants, and while you're alive, the ratio of carbon-14 in your body perfectly matches the atmosphere. But the absolute second an organism dies, that exchange stops. The carbon-14 inside begins to decay, and that is exactly when the radiometric clock starts ticking. Because its half-life is a relatively short 5,730 years, carbon-14 is strictly used for recent history. Think ancient campfires or artifacts, maxing out at around 40,000 years. Beyond that, the remaining carbon-14 is so incredibly tiny that even our most advanced mass spectrometers struggled to detect it. So, while uranium takes us back to the dawn of the solar system, carbon-14 is the ultimate clock for archaeologists studying human history.
Finally, let's pull it all together in Section 6, Choosing the Right Clock.
So when you look at it all laid out like a cheat sheet, you see why scientists have to match the half-life to the specific mystery they're trying to solve. You literally cannot use carbon-14 to date a dinosaur bone. All the carbon-14 would have vanished millions of years ago. On the flip side, you can't use rubidium-strontium to date an Egyptian tomb. Its half-life of nearly 49 billion years is so long that practically zero measurable decay would have happened in just a few thousand years. Geologists have to evaluate the expected age, the specific minerals present, and the rock's heating history to pick the absolute perfect radiometric key for the job.
Which leaves us with a truly profound question to ponder today. If Earth's rocks are constantly being melted, subducted, and recycled, literally resetting their atomic clocks over and over again, what does age actually mean in the vastness of deep time? When we measure a rock, are we dating the atoms themselves, the moment they locked together into a crystal, or just the last time the Earth violently reshaped them? The Geologist Toolkit does way more than just spit out numbers. It kind of forces us to reconsider the very nature of time, permanence, and the endlessly recycling engine of the planet we live on. Just something to think about the next time you pick up a simple, ordinary pebble on the beach. Thanks for joining me on this explainer. See you next time.